here that I wasn't that familiar with. It's a number theoretic result, and this greatest common divisor is sometimes called, I've seen it called the GCF quite a bit, for greatest common factor, GCF. All right, GCD is what I've grown up accustomed to. But in any event, we're supposed to find the greatest common divisor or the greatest common factor of two pretty large numbers, this 5-digit number and this 4-digit number. Now, there's this theorem that I'd seen and was kind of aware of. I recently proved it to myself, but it gives you a way to kind of scale the thing down, this result right here, this theorem that says the greatest common divisor of A plus some integer multiple of B is just equal to the greatest common divisor of the two numbers. And x, a member of Z, means x can be a positive or negative integer. Okay, so let's just do a concrete example right here. Now notice what we did right here. We actually subtracted off a multiple of 60 from 584. Notice that x is a member of Z, so -9 is totally legitimate. You can just think of this as 584 minus 540. And so this would equal to 44, comma 60, the greatest common factor of 44 and 60. Now the idea behind the theorem is to get it down to tractable numbers that you can, quote, do in your head. Now this one isn't hard to believe. We can be rigorous about it, but 4 is the greatest common divisor of 44 and 60. Okay, so we can write this. And this is just an example of going to help us with a larger problem. Okay, that's equal to 4. Now, a lot of you may be saying, well, we could just do this by doing the prime factorizations, and that's right. If you can find the prime factorizations of this number and just pluck out the prime factors that are common to both and then multiply them, that'll be the greatest common divisor. Okay, so you can do it that way, of course. But I just kind of like this method. I just learned it recently. Now, so let's take a look at the problem at hand. Now, this does require a division here, and so you have to be able to divide 1365 into 13923. You can do that by hand and then determine that the quotient is 10 and the remainder is 273. Using the previous result, and I won't say much about it, but you can see that the answer is 273. Now again, this computation here isn't too hard because 5 times 273 is 1365, right? So this is a fairly quick computation just mentally. So the solution, the answer to this particular problem is 273. Now I know a lot of you might be saying that, well, we already had it right here, but that's not always the case. Just because 273 is the remainder doesn't mean it's always going to be the GCD. And let me give you just a concrete example right here. 584 and this stumped me for a little while. 584 is certainly equal to 9 times 60 plus 44. So 584 equals to 9 times 60 plus 44, right? 9 times 60 is 540, and then you have a remainder of 44. Now, so you can't just haul off and say that 44 is the greatest common divisor of the two numbers. Now, if you take a look, you see, in other words, we already know for a fact that the GCD is 4, not 44, right? Okay, now, again, down here, it just happened to work out, and there's the 273, the remainder is also the greatest common divisor. It's not always the case, and this is an example to show you why it's not true. But anyway, my main intent was just to show you this nice little, I guess, reduction trick when you're trying to find the GCD. You can add or subtract multiples of the smaller number, okay, and then scale it down to a much more tractable greatest common factor problem. Now, I did prove part of this, and I'll show you why this theorem partially is true. It's kind of a neat little symbolic proof. Let's go down. If you follow this right here, these are all of this stuff just follows from the properties of the GCD, and you can read through this. It's not particularly difficult, but what we do right here is prove divisibility in one direction. We prove that the GCD of AB does divide the GCD of A plus BX quantity B. Now you can also show divisibility in the opposite direction, which would prove that the two were equal to each other. And that proves it's kind of a nice number theoretic result, but it's slightly technical. But this is kind of half of the proof. This statement, all of this stuff right here, is more or less half of the reason that this theorem right here is true. Now, just one more side. By the way, this is the answer to the question that was asked. 273 is the greatest common divisor. But the basic idea behind the spirit of this proof is just the following statement. If you have two positive integers, a and b, and you can show that a divides b, okay, this means a is a factor of b, okay, which is what we did right here. This would be the a divides b part. And you can also show that b divides a. It's an obvious but very powerful result, really, when you're trying to prove that two things are equal in number theory. Well, what's the only possibility here, folks? I'm telling you that a is a factor of b and b is a factor of a. That would imply what? A equals b. And I'm just going to do a separate video on this sometime. I did part of the proof, and I said, well, I'll just do a numerical example. But anyway, this is certainly a fact. And what we've done right here, we've done the a divides b part. That would be this. But we would have to go the opposite direction and say the GCD of the quantity a plus bx, b divides the GCD of ab. And that's about the same kind of stuff that you do going in this direction. I just kind of drifted and decided not to finish the proof. But anyway, thank you for viewing, and hope you enjoyed.